Okay, let us start another session. See this question. Find the resultant magnetic moment for the following arrangement. So we have three magnetic moments. The angle between these two is 90 degrees. Okay. So how to solve this? See, whether you put it here, basically they are vectors. Treat them as forces, So you can write here also. This. So you have to find, the resultant of these three. So take this and this. So you can apply the cos rule. You can apply the parallelogram law. Okay. So m1 will be equal to root over m square plus m square plus 2m1 m2 cos 90. It is 0. So it is m root 2. So the resultant of these two is like this. It is m root 2. There is another magnetic moment in this direction. So what is the final answer? It is m root 2 plus m. So m into root 2 plus m. Root 2 plus 1 into m, option 2. Okay, let us see this question. These are little tricky questions. Two magnets A and B are identical and these are arranged as shown in the figure. The length is negligible and in comparison to the separation between them, length is negligible means they are short magnets. Okay, a magnetic needle is placed between the magnets like this at point P, which gets deflected through an angle theta under the influence of magnets. The ratio of distance d1 and d2. So one magnet is put in a horizontal position, one magnet is put in the vertical position. Okay, so that is called the magnetic field created by this is B1 and this is B2. Now what is happening is, so here the magnetic field lines will be in this direction and here the magnetic field lines in this direction. Okay, so actually this is south and this is north and this is south and this is north. Okay, directions are not that important, but basically you can take that one magnet is being put like this in the horizontal position, one magnet in the vertical position. So obviously now these magnets are not moving, so they have been kept like that. So obviously the needle will show some deflection, isn't it? And that deflection is theta with respect to the vertical. So we have to find the ratio between the d1 and d2. So how to proceed means, you see here, so the magnet is making some deflection theta. Okay, now here the field lines due to this are in this direction, let us say d1, and the field lines of the second magnet, which is kept in the vertical position, are like this. Okay, so under the influence of this b1 and b2, this magnetic needle is making some deflection. Okay, so let us say the magnetic the resultant of these two, let us say, is b dash. Okay, so if this angle is theta, so this angle is theta, so this angle will be 90 minus theta. So can I write b dash cos 90 minus theta is equal to b1. Okay, so that means b dash sin theta is equal to b1, right? Similarly, when you resolve in the other direction, it will be b dash cos theta is equal to b2. You call this as equation 1, you call this as equation 2. Okay, so take the ratio of 1 and 2, you get tan theta is equal to b1 by b2. Alright, or b1 is equal to b2 tan theta. So this is what we have got. Now we have to eliminate this b1 and b2. What is b1 and b2? When you put the magnet like this, isn't this axial direction and axial direction of this? So if you consider this as the can you find the magnetic field of this magnet for a short magnet? So b1 is equal to, it is mu naught by 4 pi multiplied by 2. Let us say the magnetic moment, both magnets are same, So 2m by 2 small m by d cube. Okay, so which d? We have to put this d. So d1 cube is equal to b2. b2, it is for this magnet. Okay, and now for this magnet we have to take what will be the value of b2? b2 will be mu naught by 4 pi multiplied by m upon d2 cube. That will be the value of b2 multiplied by tan theta. Okay, so cancel out the common terms here. So mm cancelled. So here you are getting d2 cube by d1 cube. d2 cube by d1 cube is equal to tan theta by 2. Okay, or we want d1 by d2, so I am just writing here. So d1 by d2 whole cube will be equal to 2 divided by tan theta or 2 cot theta. Okay, so d1 by d2 will be equal to 2 cot theta to the power of 1 by 3. So option 3 is the right answer. Okay, did we do calculations part correctly? So this is okay. So yeah, now actually if you observe here, now this point, if you take this point over here, this is in the axial line of the first magnet, but when you place the magnet like this point will be on the equatorial plane of the second magnet. So that is why we have put here. Now this is the axial part, axial formula, and this is the equatorial formula. Okay, I just wanted to clarify. So we will get option 3 as the right answer. Okay, students, let us look into this question. Two small magnets, note the terms x and y of dipole moments m1 and m2 are fixed perpendicular to each other with the north poles in contact. This arrangement is placed on a floating body so as to move freely in Earth's magnetic field as shown in the figure. Then the ratio of their magnetic moments is. So they have their own magnetic moments, magnetic dipole moments. You have to find the ratios. See, there are two magnets and they have been kept like this. On a floating body. What will happen? So initially they will take some time and they will adjust themselves, and this BH is the horizontal Earth's field. So finally, they're fixated like this. So what does that mean? So finally they have come into a position of equilibrium. Okay. Now why they are coming into equilibrium? Because if the magnetic field, Earth's horizontal field is showing in this direction, where will be the north? North will show attraction towards the south, and south will show attraction towards the north. If you remember, while discussing this magnetism chapter, we have discussed this point that this magnet's north pole, it points towards the geographic south of the globe. Okay, and here the north will show in this direction, the south will show in this direction. Okay, if the magnetic field is shown like this, so you take this. How is the situation here? It is like this. In what way it is trying to rotate? Is it not trying to rotate like this? And you see this situation. Here the situation is like this. How is this trying to rotate? Is it not rotating like this? Okay. So if you call this as torque T1 and you call this as torque T2, so they are stick on to each other because they are in a state of equilibrium. So that means torque 1 must be equal to torque 2. So what is torque? Magnetic moment. Torque is basically cross product of M and B, and you have to, when you open this, so magnitude will be MB sine theta. So the angle you have to measure starting from M towards B. So if you take the first one, if you take this one, so let us say for this one M1B1, M1B sine, what is the angle here? 30 degrees. So this must be equal to M2 B. Starting from the magnetic moment, you have to take angle towards the B. So what is B here? BH. Okay. So sine 60. So B is common here, isn't it? So you can cancel out B. So M1 by M2 will be equal to, M1 by M2 will be equal to sine 60 divided by sine 30. So sine 60 is root 3 by 2 and sine 30 is half. So it is root 3 by 1. Okay. So option B is the right answer. You understood now what I have done here? I have just equated the torques, because if the system has to be in this particular position, it is fixated. It is not fixated by any glue or something like that. It is put like that. See, normally what will happen, this north and north, there will be repulsion, no? Okay, but there is north and north repulsion, then they cannot stay like this. But now the arrangement is placed on a floating body so as to move freely. Shown in the, somewhere there is a line here. You see here, they are fixed perpendicular to each other. They are fixed perpendicular to each other. Why is saying perpendicular to each other? Because the angle, the total angle between these two, how much? 30 plus 60, 90 degrees. Okay, so they are fixed like that. If you keep them normally like this, they will repel each other. So if they have to be kept like that, there must be equilibrium. That means the torques must balance themselves. Okay. So option D is the right answer. Now look at this question. A bar magnet with poles 25 cm apart and of pole strength 14.4 ampere meter rest with its center on a frictionless point. It is held in equilibrium at 60 degrees to uniform magnetic field at induction 0.25 Tesla by applying a force at right angles to the axis 12 cm from the pivot. The magnitude of the force is, see, there is a magnetic field like this, and you have kept a bar magnet like this. Let us say this is the south pole and this is the north pole. You know that magnetic field is shown from north to south, right? So what will happen now? This magnet is kept in equilibrium, and at equilibrium it is making 60-degree angle. Now if you simply leave this magnet like this, what will happen? It will tilt. It will not be in equilibrium. So in order to keep it in equilibrium, now this is the axis. So they have put a force, some force at 12 cm from the pivot. This is the pivot, 12 cm from the pivot. See, basically this is north, this is south. So it will experience a force like this, it will experience a force like this. So there will be a torque. Okay. On the magnet there will be a clockwise torque. What is this type of torque? This is anti-clockwise torque, right? It is anti-clockwise. So this force is creating a clockwise torque. So these two are balancing each other. That is why this magnet is in equilibrium. So you can write like this: the torque, which is mb sin theta, it is which type of torque? It is ACW. This must be equal to the torque created by this force, which is force into distance. Now this is clockwise. Then only the system is in equilibrium. So you have to just put the value. You have to find what? We have to find here. We have to find here the magnitude of the force. We have to find this force. So the force will be mb sin theta divided by distance. Distance is given as 12 centimeters. So let us start putting the values now. So bar magnet with 25 centimeters apart and a pole strength 14.4. So what is M value? 14.4 into the distance between the poles, which is 0.25, into B. B is this thing, your field strength, okay, into sine, starting from M towards the magnetic field. What is the angle? Sine 60 divided by D. D is 0.12. So let us just simplify this. See, we know that root 2 is equal to 1.414, isn't it? So 10 root 2, so this is approximately 10 root 2. So this is 1 by 4, this is 1 by 4. So sine 60 is how much? Sine 60 is cos 30, root 3 by 2. And this is 100 by 12. 100 by 12. 100 by 12 means 4 25s and 4 3s. See, often these numbers are given in such a way that you can make hand calculations. You don't need calculators, etc. Okay. So let us just simplify this. So this is 2 2s, 2 5s. Okay. And this is going root 3 times here. So what am I left with? This is root 2 times here. So there is 5 here and there is 125 here. So there is 125 divided by, there is 4 here, there is 2 here, and there is root 3 here, and there is also a root 2 here. So 8 root 2, and there is a root 3 also. Okay. So can you write this? 125 into root 2 into root 3 divided by 8 into 6. Okay. So the answers are in root 3. So if you keep aside this, we have to solve this. 125 root 2 divided by 8 into 6. Okay. So this is approximately 48, 50. So 50 means 125 by 50 into root 2. 25 2s, 25 3s. So 1.5 into root 2. 1.5 into root 2 means 1.5 into 1.4 you are getting now. Into this whole thing multiplied by root 3. These are options, root 3 is there. So 1.5 into 1.4 cannot be 15, cannot be 75, cannot be 25. Option 3 is the right answer.